Hello everyone, my name is Beniam and my teammates Clarence Choi, John Voder, and Keith Duong are pleased to present our project DOE Analysis of Laser Etching, examining kerf width on acrylic tabs, completed as part of Mechanical Engineering 283 at San Jose State University. To guide you through our presentation, we have divided it into the following sections. Introduction, by Me Fabrication Method, by Clarence Choi. Data Gathering Method and Data Analysis, by John Voder. Study Inference and Conclusions, by Keith Duong. The objective of this project is to examine how speed, power, and pulse per inch, or PPI, affect the kerf width in laser etching and determine the best parameter settings to achieve a target width of 0.7 millimeters. To achieve this, we used a 2 to the power of 3 factorial design to identify the significant factors and interactions affecting kerf widths. Perform analysis of variance using ANOVA with multiple factors. Develop a regression model to predict kerf width. Determine the best parameter settings for the target kerf width. Evaluate the results under a 95% confidence level with a significance threshold of 0.05. This work aims to optimize the laser etching process consistency. To carry out this study, we used a factorial design with 3 factors, speed, power, and pulse per inch, or PPI, each tested at 2 levels. Speed was tested at low and high settings of 0.89 and 0.98 millimeters per second. Power was tested at 36 and 48 watts, and PPI was tested at 500 and 1000. Each combination of these settings was tested twice, giving us 8 observations with replicates. This design allowed us to analyze the variability in kerf width and ensure statistical significance in our results.
For our fabrication method, we used a laser cutter. We designed the patterns on Adobe Illustrator and used a universal laser engraver. Hardware parameters were a 2.0 lens on the laser, and then it was a 75-watt laser, and it was equipped with a CO2 laser diode. Here's the image. Adobe Illustrator, the machine operates in red, black, and blue. So indicated in red are the cut lines that we will be making in our samples, and they are created with 2 horizontal lines, 0.15 inches long, distributed along 0.1 inches spacing, and they are lined to the right side. For the vertical line cuts in which it separates all the pieces, it's a 1.5 inch long cut distributed by 0.15 spacing aligned to the top.
For data gathering, we took the 16 samples made with the laser cutter. Each sample had 4 cuts etched into them by the laser. These would be our subject for the kerf width measurements. The kerf width measurements were taken using open source software called Digitalizer that would create a length value in pixels. We used a loaned A0055 megapixel magnification handheld microscope loaned to us by Professor Lee. After several iterations on different samples, we found that a 200x magnification and a 20 millimeter gap from our sample to the lens would allow us to acquire clear enough images to distinctly identify edges created by the laser cutter. We created an L-shaped acrylic part that would be used as a jig for alignment with the camera for all of our iterations. It was found that with this given distance to the microscope, as well as its magnification, there would be 2.58 pixels per micron. This value allows us to calculate the kerf width. For each of our 4 measurements were taken per sample, then the next sample was rotated in. On this slide, we can see our alignment bracket in the top left. In the center, the distance measured to the sample. To the right is an image of a sample. For this replicated 2 to the 3rd experiment, we generated a 2-way ANOVA to study the effects and interactions of the factors as well as identify significant contributors to kerf width variation. A total of 16 samples were used with 4 kerf widths measured per sample. An alpha value of 0.05 was chosen. The degree of freedom is 1, as this is a 2-level experiment. Looking at the largest F statistic value with a correlating p-value below our alpha value of 0.05, we see that pulses per inch is by far the most significant effect in our experiment. No other factors or interactions come close. The factors chosen for this design experiment are speed of the laser moving across the sample, the power of the laser in watts, and pulses per inch. Pulses per inch are correlated with cut cleanliness. This slide shows our main factors without interactions and their correlation to kerf width. At high level, speed and pulses per inch were closer to target, and power at low level was closer to desired. As stated in our previous slide with the ANOVA, pulses per inch alone has the most significant effect on achieving our desired 0.7 millimeter kerf width. Our interaction effects that include speed follow the trend of high level measuring close to the desired width, while power and pulse per inch trend to the lower level.
From the data collected with the different combinations of factor levels, a regression model was produced to predict the most appropriate input levels for speed, power, and PPI to achieve the desired target kerf width. The R-square value for this regression model is 95.6%. The surface plots for the combination of factors were also produced. However, based on the regression model, we only need to focus on the surface plots of width versus speed and power, and width versus power and PPI, as these factors play a more influential role in the output width. Contour plots for different combinations of the 3 factors are also produced to better visualize the different factor combinations and how they affect the output curve. Examining the residual plot, we can see that the data follows the normal probability line and has no significant outliers. This gives us confidence that our normal distribution assumptions are reasonable and applicable. Additionally, the residual versus experiment run order plot shows that there is no discernible pattern between the observations, thus indicating that our residuals are independent of when the observations occur. A plot of residual versus fitted value was also produced to allow for a visual examination of equal variance. We can see that the residual is random but symmetric across the zero line. This confirms that we have equal variance and affirms our estimate are unbiased and consistent. Recall the objective, we are set out to find the best combination of 3 parameters on the laser cutter to produce a target curve width of 0.7 mm. A 2 to the third full factorial experiment was conducted in this endeavor. A two-way ANOVA and regression model were produced, and from our analysis, we found that the input settings of speed at 0.89 mm per second, power at 36 watts, and 1000 ppi on the laser cutter gets us very close to the target curve width. For future work, we can conduct an SPC study using the suggested input parameters to quantify variance or examine the process disturbances. Additionally, we can repeat the experiment with another type of base material to determine the new input setting. Thank you for tuning in.